right? So, but you can also do the reverse bias where you change the polarities, right? In that, if you keep on increasing your bias voltage, at some point, like you see what is known as the breakdown, right? So it's like you have so many the kinetic energy of the electrons which are there, like so you're pushing them so fast that like they go and knock off other electrons which are around,
Mm-hmm.
right? So that causes an avalanche, right? So it's the same process which is used for single photon detection. So for
Mm-hmm.
example, your bias is just before the breakdown voltage where this avalanche process starts, and then a photon falling on your diode, right, which is reverse biased, so that triggers the avalanche, right? So you can get a when one single photon is absorbed, like so you get a output pulse, right, which you can shape and detect.
Hmm. So how do you know if it's exactly one photon that you're detecting and not just like two photons hitting it at a very similar time?
Right. So the good old Hanbury Brown Twiss experiment, which is known in astronomy as well. Like the idea is that like if you put a 50-50 beam splitter, so 50% of the light is getting reflected and 50% is getting transmitted. If you have a single photon, right? So if you have many photons, so half will go into one detector, which is in the reflection path, and the other half will be detected in the transmission path by the detectors. But if you have a single photon, it'll either go into the reflection or into the transmission, but not to the both the detectors. So what we do is the standard technique is to measure the so-called second order correlation function, right? Which is finding the probability of finding the photon in both the detectors at any given time, right? So when the path lengths of the reflected and the transmitted are equal, right? So that's a t equal to 0, right? So the photon can only go either in the reflection or in the transmission.
Mm-hmm.
But if you have a time which is not equal to 0, which means there can be a stray photon coming from behind or after the photon which we want to measure. So that can trigger both the detectors, both the reflection and the transmission detectors. So you'll have a non-zero probability of finding a detector in both the detectors at t not equal to 0. But at t equal to 0, you'll have only one single um, detector triggering. So the
Mm-hmm.
probability of finding photon in both the detectors will go to 0.
Mm. Okay.
Okay, okay, that's making sense. But continuing on with with these photons itself, I'm just trying to relate the art of photonics that again I know nothing of to detecting these photons. So what I guess my question can be is where does the detection of the photon, or what does the detection of the photon tell you about the interaction with these particles? Because I'm assuming what you're doing, again, completely correct me if I'm completely wrong, but I'm assuming you're like sending out a stream or maybe a singular photon interacting with some electronics and then it's being detected. So I guess my question is, what is that detection telling you? Or did I just get that completely
So
wrong? Is that not what you're doing? What is that photon really doing in the first place?
so the technique which I said is for saying whether we have one photon or more than one photon,
Mm-hmm.
right? But this photon can be used eventually for, say, for example, for quantum, like single photon level interactions, right? So when we want to compete with electronics, like when we say like photonics may one day replace electronics, like it's a far-fetched statement, but at the present, because the cost of chips, electronic chips is much cheaper compared to, because we are packing more number of transistors into the chip, right? And also the power consumption is much lower. So now we want to have processes which will work at few photon level, right? So that's one application where like we want to use low power consuming photonic uh, circuits, right? So that's one area like where these photons can be used. And of course, like for communication point of view, a single photon is always better than many photons, because if somebody steals that single photon, we know when I'm sending information to you, if somebody steals the photon which I have sent you, automatically we'll know that, like, okay, somebody is stealing the data.
Mm-hmm.
Right? So the security increases if we use single photon communication.
And so, are the complications in developing photonics, do those arise when considering the quantum effects that come into play?
I mean, you're asking about how complex it is.
Yeah, like the difficulty in developing photonics is in considering the quantum effects that kind of play with the system.
Right. So the whole game of this argument about can we have an alternative for electronics is because we're packing more and more transistors, and eventually when we go to single atom level, or so we're talking about quantum effects, right, where these devices will be interacting with each other, right? In terms of photonics, pure photonics, the problem is, if you talk about a photonic device, right? Uh, why can't we see an atom with in a microscope, in an optical microscope? It's because it's below the diffraction limit, right? Like, so we see something when we get the reflected light, right? Or at the limit of the resolution, it's the distortion in the wavefront or distortion in the optical beam, which will tell us, like, okay, there is something, some obstacle, some particle in the path of the optical beam, right? So the diffraction limit says that the particle size should be greater than or equal to lambda by 2. So if you're talking about blue light, like, so 400 nanometers, so the particle sizes should be at least 200 nanometer or so. The sizes are much bigger, right? Compared to electronics, where we're talking about 7 nanometers is the smallest feature which you have in the electronic circuits, is in the chips. So here we are talking about fundamental limitations coming from the diffraction limit, right, which puts it at lambda by 2. These are much, much bigger compared to the electronic circuits which are possible. So how do we overcome this? So one area people are looking at is these metamaterials, right? So you can have, initially people are thinking about using what are known as the plasmons, which are surface waves. So when you have a metal, you have large number of free electrons on the surface, right? Under certain conditions, so you can excite a charge density wave. So you have more number of electrons at one place and less number of electrons at the other place. And this charge density wave propagates along the interface of a metal and a insulator, right? So the metal dielectric interface. So because this charge density wave, the plasmon mode is a surface mode, which means that close to the surface, within say 10 nanometer of the surface, you have this confinement of the field going on. So from optical domain, where you are talking about lambda by 2 features, now you are confining that electromagnetic field to the surfaces of the order of like tens of nanometers. Okay. So you are bringing down the field to much smaller dimensions, which are comparable to the electronics. Okay. So these are challenges. So now how do I manipulate the photons? So we talk about these so-called metamaterials, which are designed materials with sub-wavelength featured structures or